So this is Dushan. I'm Philip. We're from the private company GoodAI. Our main goal is to research and develop AGI, and we have found some different challenges in pursuing this goal. We found a tool that we're using. This is our main tool and our method of solving some of these problems, and we want to share it with you. So this will be a live presentation of our tool called Brain Simulator. First we'll talk about how reaching AGI was the motivation, how it's a motivation for making this tool, Brain Simulator. Then we'll go into a live presentation of how it works. We will do a MNIST classifier, feed-forward network, just to show you how easy, how fast it is to build a functioning experimental model using Brain Simulator. We will do a simplified Q-learning algorithm of the breakout game. And Dushan will also show our final breakout game that's taking the inputs as just the raw pixels and already pre-learned the whole strategy to play the game. And in the end, we'll be answering questions if you have any. The task of reaching AGI, we really see it as a puzzle problem where the bits in the puzzle, there are all these algorithms and technologies that we have. The question is how to get there. Do we need to organize all these bits in some new type of way? Is it a question of these puzzle bits that we already have to have them organized correctly, or do we need to invent new bits of the puzzle to add into this whole model? And the third thing that we are experiencing is we're a team of 20 researchers already and growing. So how do we collaborate? How do we share our work? How do we make sure that we're all going in the same direction? For these purposes, we have created a tool called Brain Simulator. This is a screenshot of Brain Simulator, and as you can see, it consists of nodes and edges. You can drag and drop different technologies. It can be a neural network, it can be a visual input, it can be anything that you can imagine. We have lots of technologies already implemented, and you can see the visual representation of it just with a click of a button. You can also interact with it. You can change hyperparameters. You can see how it changes your model, how the network learns or not learns, if it's overfitting or not, and you get feedback instantly. For creating new models, this is like the second problem of the puzzle. We have template code available, and it's very easy to make interactive. Like if you want to add a hyperparameter to your model, it's just one line of code. Everything is prepared, the hyperparameter shows up. You can change it during runtime, and it's instantly shareable. Everything is modules. So once you have the platform, you just create a new module. It's not integrated, so you have to recompile everything. You just add a module. You can share the modules with everyone, and everyone can work on the same thing. And now I would like to go into the live examples. So let's start with the feed-forward network. This is the Brain Simulator, and I'm just starting up a new project. We will choose the environment here to be the MNIST world. So we will have the bitmaps and the targets as inputs. We'll be using a neural network as a classifier that takes these inputs. As you can see, I'm just dragging them. We need to set up the inputs. We will have an exposition time of just 1 because it's faster, and we need the target to be binary. We'll make a simple neural network. So just one hidden layer and an output layer. Input 1 here is really visual, and input 2 is the target, so we can name them correspondingly. Connect the hidden layer, connect the output layer, add the target. That's it. We have built MNIST classifier in like 1 or 2 minutes. Let's see how it works. This is the input that it receives. Here's an observer. And this is the target. So if we just try and step through it, we can see the handwritten input, and we can see how it's targeted. We can see what the objective is. Of course, we want to see if the network is learning. The format should be a column of 10. So let's look at the output just to compare with the input. And as expected, we have an unlearned network. It's just outputting something randomly. And as we iterate through each time step, we can see that something is happening. We can make it run fast. And now you can see it has already learned a lot about this MNIST database. How much it has learned is expressed by the error. So we have an output, which is the cost, and usually to look at it, I like to put a moving average on the cost. So we add an accumulator node and a momentum to it. And we can see what the cost is over time, what the moving average of the error is over time. And here you have a very detailed graphical overview of how fast, how quickly your model is converging, and how everything is working. To show you the modularity and how easy it is to switch these things, now we have an MNIST classifier. Let's switch this to the breakout game, because the breakout game is pretty much also based on a neural network. So I'll close down these observers. And we'll change the environment to this custom Pong world breakout game. The inputs that we'll be using, they are a little bit cheating, but this is just to show you, to give you an overview. So we'll use the ball, X of the ball and the X of the paddle. We're going to stack these to make it a unified input. Now we have the inputs set up, and the event here is the reward that the agent is getting. When we look at the world, we can see what we are rewarding. We can set that up as we go. We can train the model to get reward when it hits the bricks. We can train the model to get punishment when it loses a life, or in this case, to get the fast correlation, we will give it reward when it bounces the ball. And we would like to add some bricks to this. This is not a classifier, so we're removing the output layer and adding a Q-learning layer. The visual is now the input, And this is now the reward. Now the network is going to output a value for each action that it can take. What we're interested in is which one that has the highest number. So we'll add a node that takes the maximum value and shows which is the maximum value, and we'll feed that back into the Q-learning layer so it knows which action it took. And we'll give it to the output. Let's try and see what it does. So this is the breakout game. As you can see, it's trying to learn something. It's trying to get the reward slowly. And the learning model it's using at the moment is stochastic gradient descent. While we're running this simulation, we can change it to RMS prop. In our experience, RMS prop converges quite fast, and if you have saturated neurons, it alleviates these types of problems. You can even change things on the fly, like the training rate, or in the case of our RMS prop, the smoothing factor. And it should converge to some sort of solution. One thing we might want to add, in this case, that it's a question of exploration too. We would like to add some randomness. So we will put in here a random node. We would ask it to output an array of 3 with a constant distribution. And then we'll make a gate. Now we have the option, when we run this simulation, with the gate here, we can control how much of the output that we're getting is random, how much is exploration, and how much is actually what the network has learned. So here we have a lot of randomness included. We can make it less and less. Or if we need more exploration, we can make it even more. But that's how easy and fast it is to set up your own models. And I think Dusan would like to show how the complete breakout game looks like when it's implemented in Brain Simulator.
Okay. So good afternoon, and I'm not going to build the whole model from scratch. So first I would like to explain a little bit how the complete model works, and so it's here. And well, actually we want to, this was one of our milestones, and we want to prove that we are able to share different parts of the model among the team, and then at the end we'll be able to connect them together into something that really works from the beginning, from pixels into the end to the action, and actually have a quite complex system in a brain simulator that actually works. And so we built a model and implemented it inside a brain simulator, and there are some parts that might be interesting. So this is the overall model, and we have a, let's say, kind of body here, and we are going to grab visual data from it, and this visual data is going through image processing part of the model, where the bitmap is segmented, where kind of attention model is implemented in order to get objects from the scene, and these objects are then filled into the working memory, so the brain actually creates a mental representation of what it actually sees. And after that, in a different way, in a symbolic representation, these objects from the visual working memories feed into the goal memory, where reward and punishment signals are used to form two different memory records. So the system is trying to remember the state of the world and representation of these symbols, the content of the working memory. So the state of the world where the reward was given into the system. So the state the system wants to achieve. And on the other hand, when punishment is given to the system, so it tries to remember the state that it wants to avoid. And from these two memory records, it's possible to evaluate if you're going towards that goal plus state, or we are going towards the goal minus state. If you add some time, if you add some delays to working memory. And from that, the current state and this fitness value, it means that if we are going towards the goal plus or we are going towards goal minus, signal is fed into the neural net. And for the neural net, these data are used for creating the training pattern online in order to create actions that will lead the system towards the goal state. So if we switch to the brain simulator, well, so we can see the model real. Here it's the part that creates the content of the visual working memory. Here is the goal memory. As you can see here, these nodes, these nodes are, this is goal plus accumulator stuff. Then here is that part that creates this goal plus memory record, and same thing for the goal minuses here. And at the end, there's this action learning module where the neural network is trained for the actions that needs to be fed back into the body. So if we run it, then we can see how it works. This observer down here, this one, is showing the state of the game and the visualization of the attention system. So you can see how the system changes attention between ball pedal and the overall field using bricks and stuff. And this attention model is driven by a set of heuristic, and we're planning to extend it a little, because right now it's more like a subconscious level when you're using heuristics like if it's moving, it is interesting, or if it's a clear boundary around, it should be an object to attend to. Also, there are some more observers. For example, this one shows the similarity between the current state, goal state, this goal plus state, and goal minus state. So it means that this green curve shows the similarity between goal plus and the current state, and the red curve shows the similarity between goal minus and the current state. And essentially, if the green curve is above the red curve, it means that the system is near the goal state, the goal plus state. And here you can see the output of the neural network, and then the taken action system is performing right now. So this is the example how quite a complex model can be created in a brain simulator in order to solve the breakout game.
So we have found for our own research purposes that we have a lot of benefits with the brain simulator. The method that we're working at, we're trying to be agile, iterative, and collaborative. We can implement new things or research immediately and experiment with it. And we have milestones that we work with that are these bits and pieces of the cognitive puzzle. And we can instantly get feedback. Is it working? Can we use it? Is it not working? Do we need to research something new? Because everything is module-based, whenever one researcher in our team makes new research, it's just a module. It's instantly shared with everyone. Everyone has access to it. Everyone can continue with the same research. This is an overview of the nodes that we already have, or just some of them, what is already implemented in Brain Simulator. I'm not going to go through all of it in detail. I'll just leave it here so you can get some kind of perception. And as a kind of final note, there is one story that I would like to share with you. This is my first conference, and I came here very, very excited and thinking I'll speak with fellow researchers and I'll get new ideas and network, and it will all be very, very cool, which I still think it is. But on the first day, I met 3 different people, and as I was talking with them, and we were getting into details about research, and specifically how do you do this task, how do you do something else, how do you do your form of backpropagation, everyone just went, oh, I can't talk about that, it's a secret. Which makes me extra proud to say Brain Simulator is open source, it's freely available for everyone. We use it, we have lots of benefits from it, and if you can use it, if you can get some benefits, if we can use it to reach AGI faster, then we'll all just be better off. You can download Brain Simulator on GoodAI.com. There are tutorials. All the models you have seen here, they're there, freely available to download. There are even more models. There's a huge library of them. And that's about it. I hope you found it useful. If you have any questions,
so questions, please?
Hi, thanks for the presentation, really interesting. So can you create a model on Brain Simulator and then export like a Python code, or would that be something you guys would do?
we don't export Python code.
Like, would that be something that you would explore? Like, if I want to create a model but in Python, but I want to create a model on Brain Simulator and experiment with it. How would that?
Python bindings, right? You want Python bindings?
It's a good question. What we have done in Brain Simulator is not to export code to Python or something like that, but we have created wrappers as nodes. So we have wrapped the cafe library, for instance. You can create wrappers for different types of technologies, different types of modules, so you can work with it as a part of the overall model.
Okay, thanks.
Can you script instead of using the graphical interface?
Yes. Well, right now you cannot, because we somehow prefer let's say graphical modeling or just standard, because it's this is done in C# and .NET. So we kind of prefer using that for coding nodes. So right now you cannot, but we were thinking about adding special node, or when you can really script some specific, like experiment specific code that it's not really usable to be as a part of the library of existing nodes. So right now you cannot, but we think it's a good idea to have such a feature.
I think you should mention the XML format that you can use this as somehow scriptable approach to Brain Simulator. Like
Well, yes, but it means that well, yes, the brain files you're using as projects is a XML format, and you somehow can script or can translate a script into the brain file in order to have something that will be more in a descriptable way. But there are probably better ways how to do this, and what we want to achieve here is to really have an effective way how to rapidly experiment, create an experiment. If you have an idea, you want to really experiment as soon as possible in order to have some result, to prove something. So it will be probably better to have a scripting feature. Okay, please.
Thank you for the interesting presentation. I have two quick questions. First, you mentioned that there was a stage at which you were doing image processing and segmentation. In what way did you do that? And second, what are some of your future research directions that you're hoping to look into?
Okay, so for the image segmentation part, I might want to give a word to our expert for the image segmentation. Anza, are you here somewhere? Yes, yes.
Oh, it's okay.
Yeah, as Dushan said before, there are a couple of heuristics so far. Like for example, that it focuses on objects that are likely to move, or if it focuses on some object, then it tries to remember. Okay, I focus on that, then next time I should focus on something else, and maybe I should go back to it. And it's like a pipeline of segmentation, trying to put these segments together and doing some reasoning with these heuristics on these objects of segments. And output of that is like I have some kind of objects with some description, which is based on neural networks, and this is fed into the visual memory. But there is no additional information, what is the object, or some training database. Everything is like learning on the fly. And as Dushan also said, that in the future we try to do this like more automatically without heuristics at all, and also it's kind of like the attention will be learned basically from the memory of the network. If it is okay, or everything you ask.
And for future research, directions, what are some things?
Oh, maybe what's kind of interesting part, and I forgot to mention it, that the output of this visual part is symbolic representation of things that have been seen recently in the scene, and we are using distributed vector symbolic architecture to be able to superpose more than one object and feed it into the network together. And this is quite interesting thing we are going to improve and extend, because we think that this is the key, how to connect higher level representation like symbols that are annotated with some data, or they are created with shapes, colors, everything together as one representation of object, and you can have a superposition of these and feed them into a neural network, because it's a problem to communicate between, or to have a symbolic representation and have a neural network to work with them. So we want to explore this area, and also we want to create a cognitive architecture that will be based on that.
And regarding the future research, we're working with milestones, so we're working in lots of separate parallel directions. We are currently having milestones within walking virtual bodies, like robots. We have milestones within the games, like the games that are being played and being solved, but being able to play multiple games at a time and using knowledge from one game and transferring it into another game. We're working on memory, how you can really reconstruct things that you have experienced in the past and how you can store it. So we have lots of different parallel research areas. Yes, go ahead.
Yeah, very nice presentation. I would be interested to know what are your commercial goals? How do you plan to earn money?
This is a very good question, and this is one of the reasons I like being part of GoodAI, because we're founded by Marek, who solely owns it, and his goal is to reach and develop AGI. That is the main objective. If some part along the way we find some way that we can use it to make money, of course we'll pursue it, but only if it supports our goal. So one of these ways, which is also part of our research, Marek also owns a computer game company, is that we want to incorporate real AGI in computer games.
Okay, thank you.
So are there
Very impressive demo, thank you. I have two short questions. Well, actually one question with two sub-questions. Would you like to, will you extend this architecture to other alternative neural network or neuromorphic computing approaches like spiking neural network models or dendritic computation models, or the formats that Human Brain Project uses? What are you planning to do with regards to that?
Yes, it's good you ask. You're completely right. We are already working in many of these directions, and every time we come up with a new module and it's tested and is working, we just make it available. We put it up there for download, but as long as we're experimenting with something, we don't want to put it there until it's really working, everything is functioning. But the idea is that it's open source, so everyone who wants to contribute, everyone in the community, if anyone says, listen, I made this module, why don't we all share it?
Thank you.
Yeah. Yes. Also, and I would like to add that it's really easy to create or to wrap a new algorithm to the brain simulator. We are providing example projects. You can open it and just start writing down your own algorithm, your own method, or to create just a wrapper above your C++ code or whatever you really want. Yeah. So we are really trying to build a platform here that will allow to share our work together, so we can really create something connected and test if it's going to lead us somewhere in the AGI area, because I think we already have really interesting algorithms that are working, and connecting them might be a way how to reach some impressive goals here.
If I may, I will just answer to one of the question regarding adding modules or scripting. So it's actually possible to write your own modules, and in C# or CUDA. I mean, we prefer CUDA because it's better for performance. And we are planning to create a platform where people will be able to share these modules, something like plugin store or something like this. Except it will not be a store; it will be just some location. And I would like to add a little bit about why we created Brain Simulator and say that it's not our product, it's basically a means to create AGI. And it's like releasing it open source, it's like a side project. It's not the main thing, like we want to sell Brain Simulator or something. Basically, just to support our AGI research and development. Thank you.
So I'm kind of thinking that there are some assumptions that go into making a module in terms of the way that it's connected, because just my understanding of what's going on, you have to propagate the derivatives back, right? And so plugging in a module implies that it's differentiable and can be used with the optimization algorithms that you've also implemented or used implementations of, like this back propagation versus the other one that you switched to. And these have to be implemented globally in some way, right?
Yes, this is correct. These were neural networks, and as you were pointing out, the neural networks, they have this task flow that they go forward and then they back propagate backward. So you need to implement both the planning of the flow and to prepare it for these derivatives and propagating the deltas backward. I didn't get into all the technical details during the presentation, but I'm glad you asked now. This is the reason we had a group that encapsulated the neural network. So this particular group, it takes care of all these particular planning and tasks that the neural networks need. So if you create something new, if you create something that has some other particular needs, you can encapsulate it in a group if it's not generic for other modules, and you can do your specific planning or flow inside of this group.
Sorry to steal the microphone again. Have you considered gamifying the whole simulators for educational purposes? So like set goals and then the user has to figure out how to solve it using the model. I don't know, would that be of interest?
Well, that's two questions. The first, have you considered it? No.
All right.
But it's a very nice idea.
It just seems like because the interface is so easy to work with, it would be quite good for education as well, so people would have to, and then reach different levels and scores.
Well, actually, the philosophy of that UI and software is that you want to start with something which is really easy to use. So yes, this is like an obvious or a natural way of starting with something like neural nets, using this software and grabbing some nodes and connecting them together. So yes, I think this can be instantly used for educational purposes. But of course, if you want something just more complicated, there are ways of doing these things. But the learning curve must not be really steep. You want to start with something that will, well, grab you and will not really be annoying to use. Yeah, so that's how we're thinking about this software.
Thank you.
Sorry for stealing the mic again. I will just add one more thing that actually we kind of consider this because we have the video game business and we have space engineers and medieval engineers. Those are sandbox games. And what we plan to do in the following months is integrate them with GoodAI and Brain Simulator, so players will be able to train their AIs in the game directly. This will be for 99% of players who just want to train the AI by reward, punishment, imitation learning, and stuff like that. And the 1% of people will be able or will want to open Brain Simulator and actually start to play with the modules or maybe write their own modules and win the games. So we think this will serve the educational purpose. We actually already did this with space engineers because we added programming modules to space engineers just because we are programmers and we felt like we want to teach kids, you know, give them reasons to start programming. So, and this will be another step.
Thanks for the good work. Do you work on optimizing parallelization over GPUs?
Well, right now we are really using GPU computation when it is beneficial for us in let's say short-term way. So we are planning to do this because it's really needed when you have really big models to simulate, but we are not there yet. We are able to use our code as it is right now, but of course we are aware that some optimization needs to be done. So, well, we are using it as you're using the C# code to basically script the execution of the CUDA kernels that are behind that. But the optimization isn't really the biggest priority right now.
Yeah, thank you for your presentation and also thank you very much for sponsoring this conference. I would like to challenge you a little bit on this because what was your main motivation to completely come up with your own stack of, because there are, for example, things like RStudio, IPython Notebook and other things which together with GitHub form a very good collaborative space where AGI or machine learning or everything can be done effectively. Why do you think that coming up with a new visual programming language and a completely proprietary system is necessary, and what is your broader vision for this to in the future to outperform other well-established communities?
Go ahead. Okay, well, first we don't really want to outperform or compete with anyone. We want to collaborate with these groups. And the reason why we are building Brain Simulator is that we want to add a tool that will be really easy to use, that will lift a lot of repetitive actions and work from researchers, and that will allow you to create experiments really fast. And we thought that there is no such a tool, because sometimes it's really hard to share results and complete modules that easy how it is in a brain simulator. Because, for example, that breakout project that's quite big was built on 3 different machines, and like a week before our milestone deadline was connected just by copy-pasting into one running brain simulator instance. So this is how easy it is to really cooperate, and the cooperation and the effectiveness of experimenting, it's one of the key ideas of our workflow. So that's why we came with this one. And also we believe that this graphical UI closely connected to developing phase of the process when you're exposing hyperparameters of your models into something that can be controlled is a key. And well, we think that there are not really many tools that are capable of that.
Okay, thank you.
Thanks, it's very cool. So, are you recording the history of experiments that have been tried on the platform? And if so, are you making that available to everybody?
To a certain degree, yes. All these models that we demonstrated, we have them as brain files, and you can just load them and everything is instantly available. So when we build a model, whenever we have for our own research, for our milestones, we save the models, and they're instantly available to load and to reuse, to copy, to look at the models, how they work.
A very detailed question. The variant of C# that you use, is it Windows only, or will it run on Mono?
I believe that it's Windows only. I'm not an expert on the other, but
yeah, so please. Well, we tried to compile it mono, it works almost. But we are planning to make this tool multi-platform, so it can be used on Linux as well. Well, it will take some work, but we are really planning this.
Be careful. Unity 3D led themselves into a pretty big hole, as you know.
Yes, that's true.
Well, it's technically a 15 minutes left. So.
I've got two questions. And do you guys plan to kind of reveal some details about how you guys handle catastrophic forgetting issue? This first one. And the second one is I saw PID in one of the listings. And do you guys have any plans to have like some real-time module from like interfacing with hardware and sensors and stuff?
I'm sorry, I haven't understand the first question.
Oh yeah, like I talked to one of your associates. Was his name Eric?
Yes. Eric's there.
Yeah. And like he was so reluctant about, like there was some issue we were talking about. He was so reluctant about revealing it. So I was wondering to what degree he could speak up.
Well, anyway, I can understand the second question, and maybe Eric. Well, we are aware that the interface between, let's say, some hardware or other real things is really important, and I think there are already systems that can serve us well in this particular area. So, for example, it should be, and I believe it will be easy to create a special world, as we call it, that will just wrap robotic operational system as a part of the brain simulator. So you can design your brain and then have a world that will enter the system based on robotic operational system and control something that's behind that. So in this way you can control some different hardware, for example. So is it okay?
Yeah, but like, I mean, do you guys plan to, say for example, use this for, implement a robot right away on the fly?
Well, yes, there's a plan of creating an artificial painter that will perceive the scene and tries to reproduce the scene using the artificial hand. So, for example, using the memory and the mental model, it can paint, let's say, partially occluded things that are remembered from past, or it can continue painting. And let's say if you stick the output of the working memory back into the system, then it can create something like a dreaming machine, and then we'll be able to reproduce some of that using some motoric part of the system. So we are planning to start working on that.
I will just add that we are planning to add some integration modules, so we will make integration to maybe ROS or Gizmo or some other kind of worlds from our point of view, which is basically just a module that connects brain simulator or the brain inside brain simulator with the outside world. And right now there is a world for the Spawn game, world for Space Engineers game, and there can be also world for ROS or Gizbo or other things.
So I'm sorry we ran out of time, so other questions maybe at the cafe if you have anything to discuss. So thank you again, GoodAI.